Consider the following scenario. A boy is walking his dog through a park along a sidewalk that runs perfectly east to west. The dog is on a 10-foot leash, so the boy is always 10 feet behind his dog. When the dog gets to the intersection of another sidewalk that runs perpendicular, it spots a squirrel directly north. The dog begins chasing the squirrel, dragging the boy on a new path through the grass. Find the equation of the curve traced out by the boy as he is being dragged by the dog. Let's start by putting these sidewalks on the X and Y axes. The leash is 10 feet long, so if the dog is at the origin, then the boy is 10 feet away at the point 10, 0. Now let's pick another point on the curve and call it XY. If XY represents the boy, then there is another point on the y-axis that represents the dog. Let's call it 0A. And this is the 10-foot leash. We can use the distance formula to solve for A. The distance of the leash is 10, and 10 squared is 100. And if we plug in the endpoints, we get this. Now solve for A. When you take the square root of both sides, be careful. Remember, this could be positive or negative. In this case, it's equal to y minus a, which must be negative because a will always be bigger than y. In other words, the dog will always be farther north than the boy. It's easy to compensate for this by just switching them. Finally, add y to both sides, and now we have a. The slope of the leash must always be tangent to the curve, so the derivative of this curve is the slope of the leash at any given moment. And we know the slope of any line given 2 points is y2 minus y1 over x2 minus x1. Now we can plug in the a, and if we simplify, we get the derivative that describes the curve we are looking for. Before we try to separate variables and integrate, let's rewrite this another way. Instead of dividing by x, let's multiply by 1 over x. Then we can bring it into the radical by squaring it. And then by simplifying, we get this, which we can rewrite as 10 over x squared. Now we can multiply by dx and integrate. This will be solved using trigonometric substitution. If we let 10 over x equal the secant of theta, then we can exploit the fact that secant squared minus 1 is equal to tangent squared. And the square root of tangent squared is tangent. We also need to change the differential. We'll come back to this later, but for now, let's solve for x. 1 over secant is cosine, so x is 10 cosine theta, which means dx is negative 10 sine theta d theta. Plug this in for dx to get our new differential. Tangent is sine over cosine, making this sine squared over cosine. Sine squared is 1 minus cosine squared. If we split this into 2 fractions, we can simplify it to secant minus cosine. Let's divide this 10 to the other side for now and get it out of the way. We can make this 2 separate integrals and focus on one at a time. The antiderivative of secant is a fairly common one. It's found on most basic integration tables that contain trigonometric functions. I demonstrate how you can solve it on your own in this video, precisely at the 6-minute and 48-second mark. I'll put a link in the description. It ends up being the natural log of secant plus tangent. That gives us the first one. And if you're still watching this video, you probably already know the antiderivative of cosine is sine. And let's not forget c. Now we need to change our variable back to x. We already know the secant of theta is 10 over x. To find tangent and sine, we can construct a right triangle with angle theta. Secant is the reciprocal of cosine, or hypotenuse over adjacent. And by the Pythagorean theorem, we know the opposite side as well. So the tangent of theta is opposite over adjacent. And the sine of theta is opposite over hypotenuse. Now, if we multiply everything in this equation by 10, we get this. Remember, any constant will be absorbed by the c. To find c, we can use the starting point 10, 0. This means y is 0 when x is 10. This all cleans up to be c equals 0. So this is it. The equation of the curve traced out by the boy as his dog is dragging him in one direction. We can generalize it for any size leash, like this. This type of curve is called a Tractrix. It was first introduced in 1670 by Claude Perrault, and it was later studied by Isaac Newton and Johann Bernoulli. Thank you for watching.